In today's lesson, we are mastering the relationship between a function and its inverse. You will learn how to represent this relationship geometrically, how to map domains and ranges, and how to identify key properties such as intersections and gradient relationships. This topic is a cornerstone of the Cambridge 9709 Pure Mathematics 1 syllabus. It frequently appears in Paper 1, often integrated with calculus or coordinate geometry, and is essential for scoring highly in the functions component of the examination. To understand the connection between a function and its inverse, we must look at their graphs. The graph of the inverse function, f inverse of x, is a reflection of the original function f of x in the line y equals x. So, here are our y-axis and x-axis, and we draw the dashed line y equals x. Why does this happen? An inverse function essentially reverses the process of the original function. If the function f takes an input a and gives an output b, we represent this as the coordinate ab. The inverse function does the opposite. It takes b as the input and returns a as the output. Therefore, the point b, a, must lie on the graph of the inverse. Mathematically, the line y equals x acts as the perpendicular bisector of the line segment connecting these 2 points. By swapping the independent and dependent variables, we are reflecting the entire curve across this diagonal axis. Let us apply this geometric logic to a linear function. Consider f of x equals 2x plus 3. We know this is a straight line with a y-intercept at 0, 3. Show graph, y-axis and x-axis. Plot 0, 3. Draw line y equals 2x plus 3. To find coordinates for the inverse, we simply swap the x and y values. The point 0, 3 on f becomes the point 3, 0 on the inverse. Draw dashed line y equals x. If we calculate another point, say x equals 1, then f of 1 equals 5, giving us the point 1, 5. The reflected point is 5, 1. Draw the line for f inverse of x, passing through 3, 0, and 5, 1. Notice how the two lines are perfect mirror images. Across the line y equals x, if you were to fold the graph along that dashed line, the two functions would overlap perfectly. This symmetry is the most important visual check you have in your exam. Let us begin with a fundamental concept, specifically the mapping of domains and ranges. The swap of coordinates between a function and its inverse leads to a fundamental rule for your exams, because the x values of f become the y values of f inverse, and vice versa, their domains and ranges are linked. Specifically, the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse. Specifically, the set of all possible inputs for the original function, its domain, becomes the set of all possible outputs for the inverse function, its range. Similarly, the set of all outputs for the original function, its range, becomes the set of all inputs for the inverse function, its domain. Let's look at this mapping visually. For the inverse function, the output y becomes the input, and the input x becomes the output. In Cambridge examinations, you are often asked to state the domain of an inverse function. Instead of trying to find the inverse algebraically first, it is usually much more efficient to identify the range of the original function. The values will be identical. Let's look at an example using a quadratic function. Consider the function f of x equals x squared plus 1 for x greater than or equal to 0. We must restrict the domain to x is greater than or equal to 0 to ensure the function is 1-to-1. Otherwise, an inverse would not exist. Here is the graph of f of x. It passes through the points 0, 1, and 2, 5. To find the inverse, we set y equal to x squared plus 1. We then rearrange to make x the subject. Starting with y equals x squared plus 1, we subtract 1 from both sides to get x squared equals y minus 1. Taking the square root gives x equals the square root of y minus 1. Since our original domain was x is greater than or equal to 0, we take the positive square root. Finally, we swap the variables to write the inverse function. Graphing the inverse, we see it is a reflection in the line y equals x. Notice the points are swapped. 0, 1 becomes 1, 0, and 2, 5 becomes 5, 2. Now let's identify the domain and range for both. For the original function f, the domain is given as x is greater than or equal to 0. Substituting this into the function, we see the range is f of x is greater than or equal to 1. Applying our rule, the range of f becomes the domain of f inverse, and the domain of f becomes the range of f inverse. The values simply swap places. There are 3 advanced properties you must master for A-level questions. First, let's discuss intersections. If the graphs of f of x and f inverse of x intersect, those intersection points must lie on the line y equals x, provided that f is an increasing function. In an exam, you might be asked to find these coordinates. Instead of setting f of x equal to f inverse of x, which often leads to very difficult algebra, you should simply solve f of x equals x. This is a major time saver. Next, we have self-inverse functions. A function is self-inverse if f of x is equal to its own inverse. Graphically, this means the curve is already symmetrical about the line y equals x. A classic example is f of x equals k over x. Finally, consider the gradient relationship. At reflected points, a comma b and b comma a, the gradients of the two curves are reciprocals of each other. This means if the slope of f at x equals a is 3, the slope of the inverse at x equals b will be 1/3. Let's apply these concepts to a typical Cambridge 9709 style question. The function f is defined by f of x equals x squared minus 4x plus 7 for the domain x is greater than or equal to k. Part A asks for the smallest value of k for which f has an inverse. For a function to have an inverse, it must be 1-to-1. For a quadratic, this means we must start at the vertex. We can find the x-coordinate of the vertex by completing the square or using x equals negative b over 2a. So, the smallest value of k is 2. Part B. For this value of k, find an expression for f inverse of x and state its domain. First, we complete the square. F of x equals x minus 2, all squared, plus 3. Set y equal to this expression and rearrange for x. Subtract 3 from both sides, then take the square root. We then add 2 to isolate x. We use the positive root because x is greater than or equal to 2. Thus, f inverse of x equals 2 plus the square root of x minus 3. To find the domain of the inverse, we find the range of f. Since the vertex is at 2, 3 and the curve opens upwards, the range of f is f of x is greater than or equal to 3. Therefore, the domain of f inverse is x is greater than or equal to 3. Let's visualize this relationship on a graph. Here is the line y equals x. This curve is our original function f of x, starting from the vertex at 2, 3. And here is its reflection, the inverse function f inverse of x, which starts at 3, 2. In Cambridge examinations, students frequently lose marks due to preventable errors. Let's look at 3 major pitfalls. The first mistake is providing an incorrect domain for the inverse. Remember, the domain of the inverse is exactly the range of the original function. Always calculate the range of f of x and then simply replace f of x with x to state the inverse domain. Next, look out for sign errors in square roots. When finding the inverse of a quadratic, you often reach a step like x equals a plus or minus the square root of something. Students often forget to justify which sign they choose. You must look at the domain of the original function. If x is greater than the vertex, choose the positive root. If x is less than the vertex, you must choose the negative root. Finally, there is reflection confusion. When sketching, students sometimes reflect in the x or y axis by mistake. Always draw the dashed line y equals x first. This serves as your guide to ensure the coordinates swap correctly, such as 2, 5 becoming 5, 2. This ensures the curve y equals f of x is reflected accurately to become y equals the inverse of f of x. To maximize your marks in Pure Mathematics 1, keep these examination strategies in mind. When asked why a function has an inverse, examiners look for the specific phrase, "It is a one-to-one function." Avoid vague descriptions. Use a sketch or the horizontal line test to justify this. If a question asks for intersection points, do not set the expressions equal to each other. Solve f of x equals x instead. It is mathematically equivalent and significantly faster. Be precise with your notation. A domain involves x values, while a range involves y or f of x. If you are asked for the domain of f inverse, your final answer must start with x. Finally, for gradients of inverse functions, remember the reciprocal relationship. Differentiating the original function and taking the reciprocal is often much cleaner than finding f inverse itself. It is time to test your understanding. Please pause the video now and attempt these 3 questions. Question 1. The function g of x equals 3x minus 5 is defined for all real x. Find the inverse of g and sketch both graphs. Question 2. The function f of x equals x squared minus 6x plus 10 for x greater than or equal to 3. Find the inverse expression and state its domain. Question 3. The function h of x equals 2x plus 1 divided by x minus 2 for x greater than 2. Show it is self-inverse and explain the graphical implication. Take your time with these, and when you are ready, resume the video for the full step-by-step solutions. Let's go through the homework solutions, starting with question 1. For the function g of x equals 3x minus 5, we find the inverse by letting y equal the expression. We then rearrange to make x the subject. Adding 5 gives y plus 5 equals 3x. So x equals y plus 5 all over 3. Therefore, the inverse function g inverse of x is x plus 5 over 3. Observe the graph. We have our original line, the dashed line, y equals x, and the inverse function. Notice that the points 0, -5, and -5, 0 are perfect reflections of each other. In question 2, we have a quadratic function. To find its inverse, we first complete the square. We let y equal the completed square form and solve for x. Taking the positive square root because x is greater than or equal to 3, we find x equals 3 plus the square root of y minus 1. So f inverse of x is 3 plus the square root of x minus 1. The domain of the inverse is the range of the original function. The vertex of the parabola is at 3, 1. Since x is at least 3, the range of f is y is at least 1. Thus, the domain of f inverse is x is at least 1. Finally, question 3 involves a rational function. We let y equal the fraction and multiply across to group the x terms. After collecting terms in x and factoring, we see that x equals 2y plus 1 over y minus 2. Swapping variables reveals that h inverse of x is exactly the same as the original function. This means h is a self-inverse function. Graphically, such a function is already perfectly symmetrical about the line y equals x. To summarize the essential points from today's lesson on functions and their inverses, the graph of an inverse function is a reflection of the original function in the line y equals x. This reflection swaps every coordinate from a comma b to b comma a. The domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. Always find the range of the original function to identify the domain of its inverse. To find the intersection points of a function and its inverse, simply solve the equation f of x equals x. This avoids complex algebra and saves valuable time during the examination. An inverse function only exists if the original function is 1-to-1. For quadratic functions, this usually requires restricting the domain to one side of the vertex. The gradients at reflected points are reciprocals. If the gradient of f of x is m, the gradient of the inverse at the corresponding point is 1 over m.